Michael here. Hopefully, you know me from other office hours. I'm a core maintainer on the vLLM project. I work on a lot of things there, and yeah, excited to tell you what's new in vLLM in the past 2 weeks. Rob?
Hey everyone, I'm Rob. I'm one of the co-leads of vLLM and of llm-d. Nice to be on.
I'm Charles. I'm one of the LLM Compressor maintainers.
Hi everyone, I'm Brian. I'm a maintainer on LLM Compressor as well, along with Charles.
Great. Yeah. So as we mentioned, we're going to cover what's new over the past 2 weeks since the last office hours. We have our special topics and lightning talk for today. In terms of vLLM project updates, we have a good number of model releases, blogs, and some training and social media fun that we'll go over in addition to the latest vLLM 0.24 release. So without further ado, let's get into it. One quick note is we do have already a pretty packed future list of office hour sessions. So we have Matish from PrimeRL will be giving a talk on his RL at 1 trillion parameter scale using PrimeRL and vLLM in 2 weeks. And then we have a Mooncake vLLM llm-d deep dive from Greg and Kay there. And then we'll do a guide LLM deep dive and what's going on in the latest release there. To get into vLLM, if you're not already familiar, it's the open source standard for inference serving of large language models. It's become that because it's, of course, a permissible open source Apache 2.0 licensed project on GitHub. It's part of the PyTorch Foundation, which is ultimately part of the Linux Foundation. Governance is great. It has support from dozens of major companies, academic institutions. Of course, it was originally started at UC Berkeley from the page extension paper. And over the past 3 or so years has grown into a huge project where we have over 85,000 GitHub stars, thousands of PRs submitted every month that we try to merge in as many as possible. It's deployed on over 20 million GPU hours every day from the metrics we at least have. So it's much more in aggregate. I checked that recently. It's a pretty insane number to think about. But we have a developer Slack with over 15,000 members. So if you're interested in active development or understanding what's going on in the various special interest groups we have, it's a great place to be. We also heavily prioritize usability. So of course, when a new model comes out, particularly a state-of-the-art model, day by day, week by week, we want to make sure you can run that in vLLM on the various hardware that you want to run on, more than just NVIDIA, but getting great performance there, but also on AMD, Google TPUs, Huawei Ascend, all sorts of hardware accelerators build into vLLM ultimately as the software abstraction between how to run the hundreds of different models on the dozens of different hardware platforms. And we have recipes.vlm.ai for reference guides on how to deploy those models on the various classes of hardware that vLLM can run on. vLLM is much more than the inference engine itself. It's ultimately a vLLM project on GitHub, where we have many other projects part of that overall ecosystem of inference optimization to inference scaling and scheduling, routers and various things on top of that. So we have vLLM Omni, LLM Compressor, speculators. Obviously, we're going to go over llm-d and LLM Compressor today, but we certainly spend a lot of time building the overall inference ecosystem in the open source AI space, and we're thankful you're here to be a part of it. So let's get into what's new. You've hopefully heard the buzz since early last week on DSpark, a new speculative decoding method published by DeepSeek. They released a paper alongside a training code repository called DeepSpec and some models on the ablations they did. Ultimately, it sort of falls in line with a lot of other research in the space. But of course, as DeepSeek does a lot of engineering excellence in making that efficient and kind of a clear win to adopt over existing popular methods such as dflash. Yeah, we're really proud to say that within just a few days, we integrated support in vLLM upstream. So you can go ahead and pull the vLLM nightly or the soon to be released vLLM 0.25 and run DSpark models natively in vLLM. We've also landed in the speculators project, which is under the vLLM project for training your own speculative decoding models, support for training your own DSpark models, ultimately in a more efficient way than the DeepSpec repo itself implements, as they sort of implement offline training that requires generating all of your hidden states from vLLM to disk to then train your speculator offline. This takes many tens of terabytes of storage to hold all those hidden states across millions of samples. And with speculators, we can run vLLM as a live server, run speculators as a live trainer, and directly produce and consume those hidden states in an online training cycle. And yeah, just a tweet here on our announcement for this and some preliminary benchmarks on how we ran the DeepSeek v4 Pro reference DSpark and how it compares against the MTP modules that were previously natively in the model. We still have more work ongoing. We are still working on sort of the confidence-based pruning or truncation of tokens. So kind of having dynamic numbers of speculative tokens in the running batch in vLLM. But yeah, we're very excited to start training more DSpark models ourselves and tuning their performance in vLLM even further on more hardware platforms. I shamelessly kind of want to plug some of the work I've been focused on the last week in scaling up DSpark. I've been pretty interested in training DSpark on some of the latest frontier models like llm 5.2. And we've been posting those models on the community. You can go ahead and find the latest llm 5.2 DSpark that we've trained on the Red Hat AI Hugging Face. And yeah, I personally learned a lot through doing this. I recommend training your own speculator for, especially if you have a particular use case, like a coding agent or a writing agent. And ultimately, because of the size of training a model like llm 5.2 at the frontier level, and thankfully some great compute donations from VertiCloud, I was able to get access to a GB300 cluster and scale up this online training at over 60 GB300 GPUs, roughly 2/3 running vLLM, producing those hidden states, and 1/3 running, or not exactly that, let's say half and half, running the DSpark training drafter using speculators, and shared a lot of that with the community. And yeah, it's been really fun to do that, and particularly developing the multi-node capability of speculators so we can really get this training done very quickly with vLLM, speculators, and Mooncake working together. Mooncake, of course, letting us communicate the hidden states over RDMA, ultimately faster fabric than through storage, and of course, scaling for multi-node. So yeah, look forward to more PRs and tuning and speculators on training these models. Yeah, Chris, it was VertiCloud. They were very, very kind to fund this research and to open models for the community. So now going to go through some other blogs and announcements. Just to shout out Cohere. They shared a fun blog on how they manage their internal fork of vLLM that they use for their production service, and ultimately shared a lot of particularly the AI agent skills and workflows that they use to try and automate the upkeep of this fork while still getting in the latest and greatest updates from vLLM main on upstream. And I think many people running vLLM production obviously need to just manage their own patches for some reason if they're going to go down that route, especially with custom models. And I thought this was just a good peek into how this can be done and automated, and is ultimately interesting for us as well as maintainers on vLLM of how we can maybe better automate some of our day-to-day things, such as cherry picks for releases, testing or dealing with merge conflicts on really large changes in branches over time. Yeah, so pretty interesting in the age of agents and open source software. Next, we have some blogs from the vLLM Omni team. They've been pushing performance very heavily and large-scale inference on the leading models. So some great updates on how they've been pushing performance and reworking the architecture to better support text-to-speech inference, ultimately showcasing really impressive speedups across a variety of text-to-speech models, each with their own particular multi-model architectures, and doing some, I think, and overall, there's these really interesting profile graphs sort of walking through what becomes the bottleneck at different workloads on these various models, and how do you think about scaling up replicas, better scheduling, or sort of like pipeline parallelism, using torch compile, using CUDA graphs. So ultimately, really interesting, deep engineering work that's been validated in production. Yeah, just great to see the development of that project. And I mentioned there was another one, and here it's focused on an omni modality model, working with a thinker, a talker, and a code to wave section. So ultimately taking in any sort of modality in, taking in or producing audio out. And so there's sort of 3 clear stages in there between those different pieces, and yeah, showing how they implemented CUDA graphs, async chunking, async output, and replica scaling for the different parts of the pipeline that get bottlenecked for certain workloads. And again, just really interesting engineering work, I think, particularly for the future, the likely future of state-of-the-art model architectures as these models become more, multimodal friendly, both on the inputs and the outputs, and it becomes more of an expectation for these models to not just take in text, or produce text, but to work natively in whatever modality we want. And naturally, the form that inference takes and the bottlenecks we have to worry about changes greatly. So yeah, I really enjoyed reading through these engineering insights, and recommend you read too, to prepare yourself for the future. Next, I wanted to give a little cheeky shout out to a tweet I made last week that I wasn't expecting to get so much press, but I also wanted to give respect to removing the original page detention kernels from vLLM. So obviously, I have Woosuk's reply in here as well, where we're just deleting the original kernels that were developed as part of Woosuk's research in 2023. And we now have much, much better kernels like flash detention, FA3, FA4, flash infer kernels that give us new Cutlass kernels or kernels from Tensor TLM, generated kernels, Triton attention, all sorts of different backends, all that ultimately implement the ideas of page detention with these flexible block sizes and various other things, prefix caching and such. Yeah, I very much think Woosuk's perspective is the right one. It's really cool to see that we can retire this and that its legacy will still live on regardless. And yeah, look how far vLLM has come. So yeah, with those updates, we'll get into the actual release, and I'll kind of hurry through because I'm taking a lot of time. In 0.24, we had a pretty large release, more commits than usual, 571 commits from 256 contributors, 77 new ones, quite a lot for just 2 weeks. There we landed the Minimax M3 support with several optimizations since the day zero image we made. We also continued pushing performance on DeepSeek v4 and GLM 5.2, particularly any sparse MLA. We've been tuning the top K kernel very heavily, particularly for very large contexts or input sequences, and particularly ragged batches. So really key optimization for agentic workloads using lots of context. We've integrated new flash infer, sparse index caching kernels, and we finally landed support for SM120 for sparse MLA, so you can run DeepSeek v4 or GLM 5.2 on your Blackwell RTX cards, and people are doing on DGX Spark even if they can fit it. We've been working a lot on Model Runner v2, enabling more models by default, so supporting a lot of types of quantization, supporting Common Quen and DeepSeek MOE models running in default there. And we've ported dflash spec decoding to Model Runner v2 with full CUDA graph support on the dflash drafter, giving much better performance as we lower the CPU overhead, which is great to see. We also landed our initial implementation of dynamic speculative decoding, which is perfect timing before DSpark came and relies on that infrastructure. This initial implementation is relatively simple, but really important for ultimately serving a model with speculative decoding and now being able to scale the draft length of the speculator all the way down to 0 as you go into higher and higher batch sizes. So ultimately, you're not compromising your high throughput portion of your Pareto frontier, even while you're optimizing and maybe want to speculate 8 tokens or 16 tokens at batch size 1. You can scale all the way down as you go to larger, more compute heavy batch sizes. We landed the streaming parser engine, which is a complete rework to how reasoning and tool calling parsers work, making it a declarative state machine instead of just kind of simple Pythonic loops and regex before. This is ultimately, we think really critical for fixing issues with token streaming that's more than one token. So obviously for spec decoding or diffusion models, as well as adding parsers for many more models and various bug fixes there. This is the first model with support for diffusion gemma, or the first release with support for diffusion gemma. Beyond the day zero image we made. Yeah, very much looking forward to implementing more diffusion large language models. Since then, we added support for KV cache watermark. So there's now a -- watermark argument you can set to reserve some overhead space in your free KV cache blocks to fight against preemptions. So if you've been seeing a lot of preemptions in production from very long output token decodes, take a look at the new watermark argument. We fully migrated to libtorch stable ABI. So this means in future releases, we will look towards supporting multiple versions of PyTorch on a given version of vLLM. We won't need to necessarily pin to a single version of PyTorch, which would be huge. And yeah, we've changed how we use CUDable visible devices using a much more structured device IDs argument. And ultimately, this is needed to make vLLM work more natively with MIG and, of course, external DP load balancing at scale. Yeah, very quickly, want to really just highlight improvements on YDP. We've integrated DPP v2 on main and DBO with Nixel. We've also a key optimization for PD is implementing the Nixel KV push mode. So pushing from prefill to decode rather than pulling, improving time to first token and in very high throughput scenarios. And we're doing a lot of work on the Rust front end, still pushing through on parity with the Python front end. On the quantization side, we finally completed the migration of GGUF model support to a plugin, so we can better separate the concerns of that support from mainline vLLM concerns. And we've dealt with a few number of CVEs and security hardening. If you're a provider looking to upgrade, make sure you check out the CVEs that we've addressed if it might affect your deployment. And it would be a good reason to upgrade beyond just the general improvements we have from release to release. I'll stop it there. And now I'll hand it off to Charles and Brian for LLM Compressor.
Thanks, Michael. Yeah, so as we mentioned, Charles and I are on the model op team at Red Hat. So we're part of the team that maintains speculators as well as LLM Compressor and compressed tensors, which is kind of a backend for saving these compressed models. So today we just want to run you through very quickly some of the updates we've made in the latest versions of LLM Compressor. I followed the same format that Michael had. So 200 commits, 66 contributors, 32 new contributors. So I think we certainly not the scale of vLLM, but we're getting good contraction and good community involvement, which we love to see as well. We're starting with more on the new model support. So we're doing more than just publishing models. We're building software here, but a lot of the stuff we've done in Q2 and really in the whole quarter or the whole year is to improve our support of large models, of new models, and reducing the time delay between like 0-day release to when we publish on the Red Hat AI org space. So as you can see, Qwen, Gemma 4, Kimi K26, DeepSeek, GLM, lots of really big models, lots of models that are released in their own quantization format. So a lot of things that we've had to do in terms of the new features to kind of enable that and speed up the time between that turnover. So what that's yielded in terms of v0.11 and v0.12 are the new features to the right. So I'll let Charles kind of go through some of the new features and then circle back on some of the roadmap ahead. So let me pass to Charles.
Yeah, thanks. The DDP and multi-GPU support as well as converter entry point we're going to talk about in dedicated slides. So I'll go ahead and talk about the ones at the end first. So version 12 was pretty much just a Transformers v5 release. There was a lot of stuff that had to go on under the hood to continue to support Transformers. The way they handle MOEs is very different. In practice for users, not a lot of changes. There's a new API to enable loading the MOE modules faster and the MOE models. But yeah, these two are pretty much all under the hood. There's a massive set of refactors that are enabling a lot of these model support and things. To the left, did refactors for the observers, the lifecycle, microscale formats. And then as far as usability, AWQ is now transformed, so you can compose it with GPTQ, which allows us to unlock some new, better accuracy values. As far as the DDP and multi-GPU support though, version 11 we enabled this for a ton of different flows, long running things like AWQ that can take 8 to 10 hours for large models. You can linearly pretty much speed it up based on the number of GPUs you have available with the DDP support. And in version 12, we released model-free PTQ multi-GPU support. So that's also available to to use. So as you can see here, the memory usage goes way down, the speed goes way up, and this continues to beyond just the 4 we tested with 8 or however many you have access to. Yeah, so back to Brian.
Thanks, Charles. Yeah, so and just wanted to end on the other bullet point we had in the new features, basically what we're calling a converter entry point, converter abstraction. So this has kind of evolved over the course of really, I think about a year when we were first looking at model-free PTQ. The idea here is to operate on a model checkpoint and create something new without necessarily having to load it up as a Hugging Face model or in vLLM, so that it can be a little bit quicker for more naive compression algorithms, or as I'll show, like some new things that came up along the way as we tried to improve our support for these new models. So what started as model-free PTQ is really just operating at the safe tensor level to apply some quantization scheme in a round to nearest kind of data-free scheme. So like not using GPTQ or AWQ, but still being able to kind of rapid prototype on these things. We had set up some code for that. We found that there's a lot of overlap with some of the things we wanted to do in terms of like converting a checkpoint. So if a checkpoint is in some old format like auto AWQ or FP-quant, or in a newer format that we want to convert to compressed tensors so that we can own the load up cycle or do anything else to it further downstream, that we have this abstraction that kind of allows us to create new instances for each of these cases. So each of these links in the slides will point to an example or to a PR that's doing these. And in addition to that, from conversion also to dequantization. As I mentioned before, a lot of the models are published in quantized formats. I've linked those down below. In order for us to do anything downstream of that, in order to change the quantization format, we kind of have a separation of concerns through the LLM Compressor, through the one-shot pathway, that everything that goes in there is already dequantized or full precision. So we don't have to worry about that. So this dequantization piece is what allows us to kind of do that as a pre-processing beforehand, before hitting the LLM Compressor flow. I think we're pretty happy with the robustness of this. We're able to whip up new converters pretty quickly. A lot of these stuff, like we had struggled with auto AWQ conversion scripts with community users, but having them code to a given contract had made that a lot simpler. It's not rocket science, but I think it's a nice abstraction, and I think we're at a point where we're willing to kind of broadcast this to the community. If people are doing a lot of checkpoint level modification, a lot of things could fit in this pattern. So please let us know if that's the case. Coming soon in the next version, we want to kind of extend this, what we have with model-free PTQ, with what we're calling model-free Higgs. And the idea there is an automated selection of the mixed precision quantization config that you want according to a given budget for weights and the accuracy goals that you have. So this came out of our collaborator research group. I linked the white paper there as well, but that's kind of one of the directions we want to extend this in the near future. Yeah, and if you have, for this or any other features or questions you might have, feel free to reach out, raising an issue on our repos, or there's also a dedicated LLM Compressor Slack channel that I've linked below. Thanks for the time.
Awesome. Thanks a bunch, guys. That's a great update. So yeah, let's go ahead and hand it off to Rob for the big update on llm-d.
Yep. Thanks, guys. So first, I just wanted to talk a little bit about what llm-d is and why it's needed. So while vLLM does a really great job of optimizing performance on a single node, llm-d focuses on optimizations that can exist as you start to scale out a deployment. So there's multiple different ways people can deploy vLLM, but one of the most common ways is on Kubernetes, which is a way to scale many different applications. And for most applications, and what a lot of people get started with for inference, is the following pattern. You'll create a deployment resource, which will create multiple replica pods of vLLM, and then a service will sit in front of that deployment and requests are round robin between the different vLLM pods. This is a pretty simple deployment pattern and one that we usually see folks getting started with. But the problem with this is that LLM requests don't look very similar to traditional HTTP requests. If you think about an agentic application, you can have requests with hundreds of thousands of input tokens that take tens of seconds to process. They're heavily multi-turn, where if you're an agent and you're working in a harness, you're going to generate some text to reason, call a tool, send the result back to the model, so on and so forth, over and over and over again. And we have these two distinct phases of inference, the prefill and the decode phase, which could potentially run on different GPUs. And so LLMD's job is to really be aware of the fact that it's running an inference request as opposed to a generic HTTP request, and attempt to implement different distributed optimizations that can outperform the kind of naive deployment service pattern that you see most people getting started with. So LLMD is a distributed inferencing framework that seeks to optimize a whole cluster of vLLM pods. And LLMD does this on top of Kubernetes. We have lots of great users, between enterprises to clouds to model companies to frontier to folks running model as a service. And you can take a look at some of the adopters and some of the blogs we have on different features. But stepping way back, I wanted to talk through a couple of the different examples of features that LLMD has, which can help to optimize performance. And I'm going to go through 5 different ones here. The first and most important optimization that LLMD can do is to have prefix smart routing during an inference request. And so I have a basic architecture design here, which explains how it works. But basically, a pod gets deployed onto the cluster that has a proxy and something called the endpoint picker. And these all make up what we collectively call the LLMD router. And so when a client request comes in to this router, the EPP contains all of the special LLM serving logic. And most importantly, one optimization is prefix cache awareness. This can give by far the most bang for the buck of any optimization we have in LLMD. And in particular, the main thing that it does is allows requests to be routed to the vLLM pod that has the prefix already cached. And this is extremely important for agentic workloads, which have this heavily multi-turn pattern where potentially one single inference session can send the same context back to the model over and over and over again. And vLLM, obviously, at this point, has really robust support for prefix caching. And so the EPP keeps track of the state of the various vLLM pods and routes requests to the pod that's going to get a prefix cache hit. And this can have orders of magnitude better performance than naive load balancing, where if you have a scale out deployment of 20 pods, you're only going to have a 1/20 chance of getting a prefix cache hit if you're randomly or round robin selecting pods. And so this is really the first key optimization that we have in LLMD, is this prefix cache aware routing. Importantly, however, prefix affinity is not the only metric to look at. We also want to deal with back pressure, where if certain pods are overloaded because they're dealing with really long requests, we want to instead route the request to other pods. And so LLMD has a library of scrapers, scorers, filters. It's very configurable and can add some pretty sophisticated scoring logic on top of the pods. And we also have a more advanced mode where actually an XGBoost model is trained online. And this model makes predictions about which pod is going to get the best latency. And this is a really good feature that is used by some advanced deployments of LLMD. But this is really the first key feature, is the prefix cache and intelligent load balancing in the design. Beyond this, the EPP and LLMD and vLLM have worked very closely together to offer a KV cache management. So as I kind of mentioned before, the KV cache and prefix cache hit rates are an extremely important optimization to maintain. And inside of vLLM, KV caches are held in GPU RAM in a least recently used structure. And so after a period of time, if requests have not come back to the server we'll end up with prefix cache misses. And you might be familiar on various instances, various service providers that they offer a cache TTL where they maintain your tokens for some period of time, maybe 5 minutes, an hour, etc. And so vLLM offers an offloading connector, and some others from IBM Research have contributed this to vLLM, which offloads KV caches to CPU memory. And recently we've added in a tiering structure where the KVs can be pushed from CPU memory into various storage systems, both local NVMe or remote network file systems like Ceph or Lustre, and so on and so forth. And then the EPP needs to be aware of this. So we support tiered prefix cache affinity in the EPP, which allows us to route requests to pods and try to land them on the ones that have the KVs in the GPU memory, and then if not, in the CPU memory, and so on and so forth. So this kind of KV cache management is a really critical deployment pattern that's useful for expanding the pool of KV cache size and increasing the time that KV caches remain in the memory such that we can avoid recomputing. Another example feature that we offer in llm-d is something called prefill decode disaggregation. This has been a very hot topic in the open source ecosystem for a while, but what prefill decode disaggregation does is it separates the prefill and decode phases of inference into two separate replicas. So we'll have a prefill worker and a decode worker. The EPP is aware of whether vLLM is configured in PD disaggregation mode, but what's very, very nice is we have a very composable situation. So when selecting which prefill worker, we can use all the same logic of prefix cache affinity to select the proper prefill worker and the proper decode worker. And very importantly, the KV transfer, where we move the KV cache from the prefill pod to the decode pod after we process the prefill, happens over accelerated networking. So we've been in vLLM supporting a couple of different transfer engines. The one that we focus on the most in llm-d comes from NVIDIA Dynamo with Nixel, which supports multiple different transport options, but in particular UCX, which pulls the KV caches over the InfiniBand networking. It's definitely a bit challenging to get these accelerated networks working on some clouds, but at this point, PD has been deployed in many of vLLM and llm-d's largest users, which really, really helps to improve quality of service by allowing the prefill work to not interrupt the decode work. And then beyond this, as we think about large models like GLM, where they might not even fit within a single node, or where we want to increase the KV cache size as much as possible, llm-d supports wide expert parallelism, where each replica, where a single logical instance of vLLM is spread over multiple pods. We use an API in Kubernetes called leader worker set, which allows us to co-schedule multiple pods together. And these pods are part of the same PyTorch process group, which allows attention to run independently, and then the expert layer to run as part of a single forward pass. This composes naturally with the prefill decode disaggregation that we have. And I'm going to cover this in a bit more detail in a second when I talk about serving GLM. This is another really important feature that allows us to serve the largest models over multiple nodes. Beyond this, llm-d also includes features for dealing with fairness and priority. I've noticed recently some cloud service providers offer things like provision throughput or different quality of service tiers like premium, standard, and fast. And the EPP includes capabilities that enable you to build something like this. In particular, there's a saturation detector, which can be configured to determine when the vLLM pods are oversaturated. And then requests will start to queue in the EPP. We call this feature flow control. And what this enables is for you to offer different quality of service to different users. So maybe you have a customer-facing application, tenant B, and a developer, internal developer application called tenant A. In a period of time where, or paid and unpaid users, for instance, in a period of time where there's a lot of load, we can choose to process the high priority requests before the low priority requests. And so the EPP's flow control feature implements this saturation detector where we'll start to queue requests as the traffic increases, and then we'll dispatch requests in order of priority. So this is a really, really cool feature that can be used to enable these quality of service or things like provisioned throughput that a lot of service providers want to offer to their customers. And beyond this, there's also batch capabilities in llm-d, which composes very nicely with the intelligent request queuing. So a very common pattern that we'll see is that users will have online use cases and offline use cases, such as batch jobs, which are often either background agents or things like evaluation jobs or reinforcement learning jobs. And in llm-d, we have a component called the llm-d async processor, which basically is a stateful component that will dispatch requests. It will talk to the EPP and probe the EPP for saturation detection and then dispatch requests. The EPP treats these as low priority requests, such that if there's online traffic, they will be prioritized over the offline traffic. But this allows you to make progress on the offline batch workload without starving the online requests. So we have some users who run shared endpoints that serve production traffic, and then they're able to put batch workloads onto that same running instance without having the batch workload completely oversaturating the online workloads. So this is a really nice feature, a nice application of flow control into the system. That's the overall. These are some examples of features we have in llm-d. There's some other interesting stuff related to auto scaling. We have some collaborations and are adopting things like Dynamo's Model Express for fast startup. But these hit on some of the key optimizations that we have in the project, which are all focused on how to serve inference as efficiently as possible. So a great application of this is for serving agentic workloads. And so I think Cam's on the call, but SemiAnalysis has done a nice job of creating an agentic benchmark called AgentX, which is a Claude Code traces. So it simulates what it's like to run a service that's backing Claude Code. These workloads are agentic. And so what this is characterized by is having very, very, very high multi-turn. So you'll see the same context being sent to the model over and over and over again. And also these requests are very long. So a lot of times you'll see benchmarks with 1,000 input sequence, 1,000 output tokens, or even 8,000. In comparison to long context serving, an 8,000 input sequence request is just actually not that long. The requests in a Claude Code trace can easily average 100,000 input tokens. And so a lot of the features that we have in llm-d, such as prefix affinity, such as YDP, are really, really useful for serving this type of agentic workload. And so I'm going to talk about how to serve GLM 5.2, which is obviously one of the coolest models today on H200s using llm-d. An example, and just for some context, why do we need YDP for serving these large MOE models? The first reason is that tensor parallelism, which is the way that we typically deploy the llama-style dense models, works great for single node, but doesn't scale to multi-node. And so every layer, when you deploy with tensor parallelism, uses a column parallel matrix, a row parallel matrix, and an all reduce. And we do this in the MLP, and we do this in self-attention. And so twice per layer, we have an all reduce. And this all reduce is very, very bandwidth intensive because every rank is talking to every other rank. They're all exchanging all the same information with each other. And so this is not going to scale to multi-node where we are going to be sending the data over the network as opposed to over the NV links in the GPUs. Additionally, when we deploy with tensor parallelism, the MLA style models have a huge issue. When we look at llama style models, the GQA attention, they have KV heads. and there's actually 8 KV heads. And the reason for this is that the KV heads are the dimension that you can shard the KV cache on. When we compare this to, and so the KV head 0 goes on rank 0, KV head 1 goes on rank 1, so on and so forth. When we look at MLA models, there's a single latent compressed KV vector, and so there's actually no dimension to shard this on. And so when you deploy a model like GLM or a model like DeepSeek with tensor parallelism, we actually will have 8 copies of the same vector, obviously dramatically reducing the number of KV blocks that we can fit these massive requests into. And so the way to deploy and get around these problems, and if you remember the original DeepSeek design, is using something called BP attention EP-MOE. Data parallel attention runs basically a single logical instance of vLLM on every rank. It manages the KV memory. And then we do a dispatch operation after the MOE router, which let's say rank 0 got routed to expert 2 and expert 4. We do this sparse all-to-all, which sends the request to rank 1 and rank 3. And so this is a sparse operation, meaning we're only sending a small amount of data. And so these dispatch combine operations can scale well to multi-node, whereas the all reduces cannot. And so this design where we have DP attention allows us to only have 1 copy of the KV vector for every token. So we get much, much more effective KV usage per token. And because we're able to scale this over multi-node, we have only 1 copy of the experts over the whole logical replica, meaning all the rest of the RAM can be allocated to KV caches. And so this is a really useful setup for dealing with agentic use cases, because when we have a model like GLM, where it's 700 billion parameters or so, we're going to consume 700 gigabytes of RAM. That leaves only very, very small space for KV caches, even on an H200. And so to fit this model and to effectively utilize it, we need to make sure we have enough KV cache space to hold all that GPU RAM. And by deploying with YDP, we get both of these things. And so in this setup that I'm going to show, we have the following situation. We have 1 decode replica, which is spread across 2 pods. So if we see, I just catted out the current state of the cluster. So we have 1 decode replica, which is expert parallel 16. So it's a single instance of vLLM deployed over multiple nodes. So there's 1 pod on node 1, on node 2, and then there's a leader worker set, which co-schedules these together. And then we have 2 replicas of EP16 prefill. The astute reader or the astute listener will notice that it's very, very important, because we're running with DP attention, that we route requests to the proper DP rank for KV cache affinity. And so this is actually something that we support in the EPP, where the EPP can target a specific DP rank. This is called DP aware scheduling. And so we deploy the vLLM pods. It creates 8 API servers per pod. Each API server hits a specific GPU, and the EPP can then route requests specifically to a rank that has the KV cache. And so then what we see is, when we look at some of the data, what we can see is that this is really, really important. The top chart, you can see the KV cache hit rate. And we can see that for these multi-turn workloads, we're able to hit 90+% prefix cache reuse. So in this agentic workload, there's really, 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 really high reuse. So in this middle row here is the throughput per, this is on H200s. This is on H200s with NVLink in between the nodes, within a node, and InfiniBands between. And this was on CoreWeave Kubernetes. And so what we see is that the vast majority of the tokens are cached. And so this kind of prefix awareness is really, really, really important. And we're able to kind of keep the TTFT pretty low, under 3-second median. Then the other point to make is, and I think the semi-analysis guys have done a great job of showing off the trade-off between interactivity and throughput. But one very important thing to be aware of is that as you increase concurrency, so as you increase the number of concurrent requests on the GPU, you will see more throughput. So you can get more tokens out of your GPU, but the latency per user will go down. So like in this case, we can see that for DeepSeek V4 Pro, I think this is on a B300, if you're targeting a latency of 50 tokens per second per user, you'll be able to get around 2,000 tokens per second per GPU. So you'll need, versus if you target latency of 25 tokens per second per user, will get something like 4,000 tokens per second per, you'll maybe get something like 4,000 tokens per second per GPU. And so you can see this very clearly in the AgentX traces. So I ran, these bumps are basically different runs with different amounts of concurrency. So we have 25, 50 concurrent, 100 concurrent, 150 concurrent, 200 concurrent. And what we can see is that the output tokens per second per GPU. So this is the y-axis, the throughput. As we increase concurrency, we get more tokens per second. And for as we increase concurrency, latency drops. So we go from 75 tokens per second per user down to like 50 tokens per second per user as the concurrency increases. And so for comparison, I went on to OpenRouter, and they have some really great stats about what latency various providers have. And so for instance, for Z.AI running this same GLM 5.2 model, they're getting about 50 output tokens per second per user on OpenRouter, and it costs $4.40 per million tokens. On this setup, we at 50 tokens per second per user, so let's say this is like 55, we're getting around 400 tokens per second per GPU. And so what we can basically see is that if we get 400 output tokens per second per GPU at 50 output tokens per second per user, and if we assume that the GPU costs $3 per hour or so on reserve pricing, this effectively translates to around $2 per million output tokens. So this overall llm-d vLLM stack is cheaper to run than consuming a shared endpoint. Obviously, it's not quite a fair comparison because this is at 100% utilization and so on and so forth. But I wanted to make the point that just with this open source stack of vLLM, llm-d, running this agentic workload, you can be pretty competitive, and with reasonable assumptions for the GPU pricing. This is what a kind of 1 year to 3 year reservation costs. You can build a system that's pretty competitive with where the market is kind of serving these models today. Yeah, that's kind of what I had to say. And all of these optimizations are critical, right? Like if you don't have prefix cache awareness, it doesn't work. Like you're going to spend all your time recomputing the prompts. If you don't have PD, you can't deploy with YDP. If you don't have YDP, you don't have enough KV cache space to fit all these requests. And so all these optimizations stack up to make it possible to serve the hardest possible workload, which is these really, really long context agentic traces for a big model on H200s. So this is kind of what I wanted to show, is how all these different optimizations layer on to enable a system that's competitive with where frontier model servers are at today. So thank you all very much. I know I probably went a little bit long, but I appreciate everyone listening.
No, yeah, we're at perfect time basically. Rob, I was wondering if you would cover one more slide right after this.
Yeah, we also have added llm-d to InferenceX. So Ezra has done a great job of delivering our first submission, and then we're very excited about AgentX and how it can show off all these different features, from prefix awareness to YDP to things like KV offloading, which isn't really too much explored in the current setup that I showed. So yeah, we love semi-analysis, and take a look at our submissions.
Yeah, thanks a lot. There were some interesting questions in the chat we can maybe go through first. Yeah, Bala, do you want to say like which hardware you were asking about? Like, yeah, I mean like the GPUs were involved had NVLink between them if on single node, but for multi-node like PD, they had InfiniBand, not like NVLink. Okay.
No, makes sense. Yeah, I think Robert answered it during while his presentation too. So yeah, all good. Yeah, thanks.
Okay, yeah. Any other questions people want to ask? Feel free to mute or...
I had one more question. I think it's from an outsider point of view, right? Like vLLM production stack and llm-d, like how we should see it, because there is some overlapping functionality. Yeah. So I'm trying to understand how we combine them, or how do we consume it?
I think that, so I personally don't know too much about production stack. So I don't really know how to.
Okay. Okay.
I think of them at like they're solving a similar problem. So I think it's probably more of an either or versus use them together. So yeah, I don't, but I do think that production stack supports like the gateway API inference extension. So like the one thing I wanted to mention is, so this like the way that this all
Mhm.
works is, I kind of glossed over this, but like technically the way that this works is there's an API called an inference pool, which is kind of like similar to a Kubernetes service in the sense of like you discover pods through Kubernetes labels, and then there's something called the gateway API inference extension, which is basically how the inference pool gets connected to the EPP. And then that allows you to hook the EPP up to various Kubernetes gateways.
Gotcha.
And so if production stack supports the concept of inference extension, then it's possible,
It should work together. Okay.
that some of the functionality in llm-d could be used.
Intersected, yeah. And one more, I think we're running out of time. One last question. I think llm-d, I heard you say it supports gang scheduling such a way that if there is no, like if you have to deploy this and X number of prefill that can decode, if all of that is not available, it's not going to launch it, right? Is that implemented? Yeah.
So llm-d project doesn't include deployment APIs. So like in the examples, like you can deploy with it's agnostic to like how the servers are deployed. In a lot of our examples, we have just using deployments to do that, for instance. But you could deploy with something like NVIDIA Grove.
Yes, that's what okay. So I would need
like,
it. It's not implemented in this. Okay, perfect. All right.
Yeah, it's not like we don't have like llm-d as a project is unopinionated about how you deploy the servers. It's kind of like, and so what this means is we can compose the project with all sorts of other ways to deploy. I like leader worker set, which is useful for like very homogeneous clusters. Grove is really going to be useful for like clusters, especially GB200, GB300, where maybe you have some topology awareness. There's other sorts of schedulers out there. All of those can work with vLLM. But one thing I would mention is like for some like more complicated flows. So for instance, for like PD disaggregation, you want to be careful about how this, like some of the operational flows about like how to roll out a new version where you don't want to select pod A and pod B with different versions of vLLM. We've worked with some folks in the community to develop this thing called the disaggregated set operator, which is intended to kind of solve this problem. So this is built into leader worker set, for instance. So I wouldn't say that like we have a hard deployment API, but like we do work with other communities to try to like develop, give requirements that can help to achieve things like what you're talking about.
Okay, super. Awesome. This is very useful. Thank you so much. Thank you.
Awesome. Great questions. Well, yeah, we are unfortunately over time. Thanks a lot to Rob, Brian, and Charles for stepping in and giving us a great update on the various related projects to vLLM. As always, thanks for being a part of the community. We'd love for you to continue being part of the community in a even greater capacity if you can. Contributions are always welcome. Join the vLLM Slack if you have any questions or want to get involved in stuff. Yeah, there's lots of learning resources, and yeah, the power of the community is what makes open source software good, successful, and ultimately rising tide raises all boats. And yeah, that's all we have for you this week. We'll get to you in 2 weeks with a deep dive in PrimeRL. And yeah, hope to see you then. Hope you have a good 2 weeks. Take care, everyone. Bye-bye.